In today's episode of One World, Your World, we're going to talk about the greenhouse effect. This is topic 8.5, and we're going to start by looking at just how much energy do we get from the sun. The sun radiates approximately 4 times 10 to the 26 joules of energy per second, but keep in mind that this energy spreads out in a sphere, so we certainly don't get that much by the time it reaches the Earth, which is about 1.5 times 10 to the 11th meters away. The power per square meter, which we call intensity, is about 1,350 watts per square meter. Okay, so that's kind of our daily average, but it's not consistent. It's not always the same. It's what we call the solar constant, even though it's not the solar constant. And over the course of a year, it ranges from about 1,038, so a little over 1,000 watts per square meter, to almost 1,400 watts per square meter. And that's primarily because the change in the distance from the Earth to the Sun, because of the eccentricity of the Earth's orbit, since we're getting a little closer and a little farther away. From that energy, we then get some of it that's reflected back out, and some of it that gets all the way in and gets absorbed by the Earth. So the ratio of the reflected radiation to the incident radiation is what we call the Earth's albedo. And the albedo varies depending on the surface type. Darker surfaces, hopefully we know, absorb more energy. Lighter surfaces reflect more. It's essentially the percentage of light that gets reflected off. As we said, it's going to change from location to location. Things like snow and ice have much higher albedos than vegetation and dirt and things like that. Dirt, especially darker dirt, has a very low albedo, but actually water also has a very low albedo. It absorbs most of the incident light that shines on it. If there are more thicker clouds, that then means a higher albedo in the atmosphere, and it's generally lowest at the equator, and as we get to higher latitudes, we generally have higher albedos. You think about what there is near the equator. There's a lot of water. There's a lot of dark green lush forests. As we get further north, you get sparser forests, and as we get extremely far north, you get much more ice and snow. So we see that trend of a decreasing albedo. The average mean for the Earth is about 0.3, so about 30% gets reflected. This little chart just kind of shows us some average albedos. You can see that there are ranges for different things. Looking at snow, old snow versus new snow, ice. Down at the bottom you have water, dark wet soil, forests. Those all have very low albedos. They don't reflect very much of the sunlight. They absorb most of it. Now this is going to impact the amount of energy that is going to be absorbed and then re-radiated as infrared radiation. And we'll get to that in a few minutes. But the average temperature, if we compare the Earth to the Moon, the Earth is around 16 degrees Celsius, while the Moon is negative 18 degrees Celsius. So that's a pretty significant difference between the two, even though they're roughly the same distance from the Sun, and even as the Moon spins around, sometimes it gets a little bit closer. The reason for this is because of the lack of atmosphere on the Moon. Because the Moon doesn't have an atmosphere, it doesn't have anything to trap the solar radiation in, and so it all just hits and bounces back out. And you don't see any real change in the temperature on the Moon. We have what are, and actually at this point kind of disparagingly called, greenhouse gases in our atmosphere that cause what we call a greenhouse effect. If you've ever been in a greenhouse, It's generally a big glass building that's designed to stay warm so that plants can grow. Lets a lot of electromagnetic energy in, and it holds it and it traps it in. Our greenhouse gases in our atmosphere are nitrogen, oxygen, water vapor, carbon dioxide, methane, and nitrogen monoxide. The final three are what are primary greenhouse gases. And while in most normal talk these are looked down upon, if we didn't have the greenhouse effect, if we didn't have these gases in the atmosphere, then there would be no life on the planet, because the planet would be too cold, it would be barren, it would be like the moon, it would be like living on the moon. So, for all those people who talk badly about the greenhouse effect, defend it. Say, the greenhouse effect is good, without it we'd be dead, you wouldn't be here, so be thankful for it. These greenhouse gases, what they actually do is to absorb the outgoing radiation and re-emit some of it back towards the Earth. They're kind of trapping in those electromagnetic rays. They're trapping in that solar radiation. Our gases absorb most of the infrared radiation and the ultraviolet radiation before it actually even reaches there. So most of the radiation, a lot of the radiation, doesn't even make it to the surface. Visible light is absorbed and it's emitted as long-wave infrared radiation. So what's going on here is that the atmosphere, the clouds, and things like that block out a significant amount of the solar radiation that's incident upon the Earth. They reflect back or absorb a lot of the gamma radiation and the ultraviolet radiation, visible light, some UV radiation, and some other wavelengths that get through to the surface. Now, once it gets to the surface, some of it gets reflected, depending on what the actual nature of the surface is at that point. Some of it gets absorbed, and so what gets absorbed then actually gets re-emitted by the surface of the Earth, by the material on the surface of the Earth, and it gets re-emitted as infrared radiation. Now, if you remember what we perceive infrared radiation as, we perceive it as heat. That infrared radiation then gets re-emitted back into the atmosphere, and some of that helps to warm the surface of the Earth. Some of it gets absorbed and re-emitted by the greenhouse gases, and then it gets re-radiated back towards the surface of the Earth, so it's not allowed to escape back out into space. So our sun shines down on us, and so here we have three big arrows. Initially, some solar radiation is reflected by the clouds in the atmosphere. Some of our infrared radiation gets through, hits the Earth, gets reflected back, and passes back out of the atmosphere. And then still some more of it gets through to the surface of the Earth and actually gets absorbed by the surface of the Earth, about half, warms the surface, gets then re-emitted as infrared radiation, and then is reflected back towards the surface of the Earth. So that heat is kept in. It's kept in the atmosphere. It's kept near the surface of the Earth, where it keeps us nice and toasty warm. Here you'll recognize a delightfully complex Sankey diagram that tries to break down what's happening to all of our solar radiation. So when it's all said and done, here we have 342 watts per square meter of incoming solar radiation in a given area. 77 of that 342 gets reflected by clouds in the atmosphere. 30 of it gets reflected by the surface. 67-ish gets absorbed by the atmosphere. And then you have about 168 that gets absorbed by the surface. So as we said, a little bit more than half. And don't worry so much about the specific numbers here, just notice the relative size of the amount. And then you have some that gets radiated out. Notice the surface radiation is actually, in this case, larger than the incoming solar radiation. And if you think about why, it's because, and thankfully so, the sun is not our only source of energy. We have this molten liquid center of the Earth that's actually warming the surface of the Earth from the inside out as well. And so you get some energy being radiated out that comes out from the surface. So we've got a variety of ways here. But you can see that there's a lot of things going on, a lot of radiation and absorption and emission and reflection going on with all this energy that's surrounding the Earth. Now let's look a little bit more closely at our individual greenhouse gases. First, the most talked about, the most glamorous greenhouse gas is our carbon dioxide. And it is definitely the largest contributor to the greenhouse effect. It comes naturally from respiration of living organisms, from organic decay, things like forest fires and volcanic activities, all naturally put carbon dioxide out into the environment. And then, of course, man-made activities like burning fossil fuels also contributes to that. Then we also have methane, CH4. Primarily it's from decaying vegetation, but also you get it from mammals removing it from their digestive systems. You may have occasionally heard that one of the biggest contributors to greenhouse gases are cows. Not really true, but there it is. Then we have water vapor. Again, it's just naturally found in the atmosphere as part of the water cycle. And we also have nitrous oxide, or dinitrogen monoxide. And then finally we have O3, which is ozone. It was depleted a while back because of the widespread use of chlorofluorocarbons, CFCs, in aerosols. That's not an issue anymore. It's not as much of an issue, the CFCs. They've been banned pretty much worldwide. They don't get used anymore. And so the ozone layer is slowly starting to repair itself. It's something that's naturally generated. It's produced by sun on oxygen molecules. It's basically gives them some extra energy. They're able to bond to two other oxygens instead of just the normal O2. And so those are our greenhouse gases. Those are the contributing members. So when infrared radiation shines down, it gets absorbed. Sometimes it gets absorbed, sometimes it gets reflected, sometimes it passes through. But when it does get absorbed, it causes molecules to vibrate. It causes, we talked about molecules absorbing electromagnetic radiation, and they turn that becomes kinetic energy in the molecule. So it absorbs electromagnetic energy. It becomes kinetic energy in the molecule as the molecule vibrates. And those modes of vibration, we talked a little bit in simple harmonic motion about natural frequencies and resonant frequencies. And so that's kind of what's going on here. These greenhouse gases have natural frequencies that are the same as the incident radiation. And so the molecules, the greenhouse gases, are significant because they have those resonant frequencies that correspond to infrared, some of the wavelengths of infrared radiation, and you get a resonant effect. When those molecules absorb that energy, they take it in, and just like when we talked about the photoelectric effect and energy being absorbed and re-emitted, that energy actually then gets re-radiated back towards the Earth. So these greenhouse gases absorb the energy, they start to vibrate, they start to shake around a little bit, and then they re-radiate it back towards Earth. So it keeps that energy near the surface of the Earth. And they have these specific vibrational modes, as we said. And here's a couple, just some examples. Here's N2 and O2. They each only have one. They're pretty basic molecules. Something like carbon dioxide, though, actually has three. You can see this top one, it's the two oxygens on the outside oscillating back and forth. The middle one, the carbon, is oscillating as well. And then in this bottom one, it's kind of an up and down type oscillation. All three of those types of vibration all have different resonances. They have different resonant frequencies, and so carbon dioxide will actually absorb three different wavelengths in a resonance way. Water, the same idea. Methane, has even more vibrational modes, as they're called. So what that means is that they can potentially easily absorb multiple electromagnetic wavelengths. Not all of them are correspondent to our infrared radiation, so they don't all get used. They're not all what we call infrared active. But the more modes of vibration that a gas molecule has, the more likely it is it's going to be able to absorb those infrared frequencies. And here, if we look, these are our three big ones. Methane at the top, nitrous oxide, oxygen and ozone, carbon dioxide, water vapor, and then the bottom one is just the atmosphere in general. And what you should notice, our y-axis is the percent of radiation absorbed. So the peaks mean that it absorbs more of that wavelength. And notice that it's all or primarily down in the infrared end of the spectrum. Hey, that's our heat. Those are the infrared wavelengths or what we perceive as heat. So methane, nitrous oxide, oxygen and ozone are really the exceptions. They've got this big chunk that's up here in the ultraviolet section. But for the most part, they're very heavy in the infrared section. Water vapor can absorb, because it has a few more vibrational modes, it can absorb a little bit more. But you can see where those resonant frequencies exist. Anywhere there's these peaks, those are resonant frequencies for that particular molecule. Now, this whole idea of absorption and emission and what absorbs and what doesn't leads us to this idea of black body radiation. I think we touched on it a little bit back in our thermo unit, but it's the idea that darker objects are going to absorb more electromagnetic radiation. Shinier, brighter, lighter objects are going to absorb less. And when we're talking about a black body, we're talking about something that is an ideal absorber, or it absorbs 100% of incident radiation. Everything that it absorbs, everything that hits it is going to be absorbed. The other part of this, though, is that the better absorber of radiation that an object is, the better emitter it is. So if something is able to absorb 100% of the infrared radiation that hits it, it's also then going to be a perfect emitter, and it's going to re-emit everything that it absorbs. So the better absorber something is, the better emitter it is. Something like blacktop. Okay, blacktop does a very good job of absorbing thermal energy, and then you go out and you can feel it just radiating off. Just the heat is just burning off of the blacktop because it's re-emitting it so well. And there's a specific relationship with black bodies between, let's move this, between the wavelength and the intensity. And this actually is one of the ways that we can tell temperatures of stars is related to the wavelengths of light that are being emitted. So hotter objects, essentially what we have, you see our 4 different lines here. This lowest line down here is the emission spectrum for an object that's about 3,000 Kelvin. So you can see it doesn't have very much intensity, it doesn't emit very much light. As we increase the temperature, and you can kind of follow this curved line here, by the time we've doubled the temperature from 3,000 to 6,000, now we're glowing. And you think about like incandescent light bulbs. They have to get really, really hot to emit visible light. They have to get into the thousands of Kelvin. But notice that even for these very, very hot objects, where is the majority of the electromagnetic energy being emitted as? Longer wavelength infrared radiation. That's why even our incandescent light bulbs, for as much light as they emit, most of the energy gets wasted as heat. And that's a big part of why incandescent light bulbs are so energy inefficient. Our sun is about 6,000 Kelvin, and so that kind of gives you an idea of where we're at with the sun. Obviously, our incandescent light bulbs are not that hot. But our sun it's hot enough that it emits pretty much all frequencies of radiation. Now, the idea of relationships between temperature and energy was primarily studied by a couple of scientists, Stefan and Boltzmann, and they developed what's called the Stefan-Boltzmann constant. And they found the relationship here that says the total area under a spectral emission curve, which is, let's say we're looking at the 5,000, that's all of this in here. That total area under a spectral emission curve is the total energy radiated per square meter per unit of time. And we call that E. And it's directly proportional to the 4th power of the temperature. So you can find the amount of energy radiated per square meter per unit time if you know the temperature of an object. It's E equals this little letter down here, it's a Greek letter, times T to the 4th. And that little letter is called the Stefan-Boltzmann constant, and its value is 5.67 times 10 to the negative 8 watts per square meter per Kelvin to the 4th power. And so the power radiated by an area A is then the area times the Stefan-Boltzmann constant times T to the 4th. So if we know the surface area of an object, like a star, and we know the temperature of that star, we can calculate the power radiated by that object. Our black bodies are ideal, so when we look at them, we can kind of see how things should be. But then when we look at actual objects, we know that they're never going to live up to that ideal situation. Just like when we're talking about things that are moving, we don't always take into account friction, but in the real world we have to. And so in the real world, we have something called emissivity. And emissivity is the ratio of the amount of energy radiated by a body to the amount that would be radiated by a black body at the same temperature. And because a black body is the perfect situation, or the maximum, you're never going to have a number greater than 1. The closer to 1, the closer it is to ideal. If something had an emissivity of 1, it would be an actual black body. And so the closer to 1, the more ideal it is. And if we put that into our Stefan's law, then our power is actually equal to the emissivity times the area times the Stefan-Boltzmann constant times the fourth power of the temperature. And so that E, that little e, gives us the actual power emitted by an actual object related to a black body. And if we look at the emissivities of some common materials, you can see that mercury and tungsten have fairly low emissivities. Water tends to be high. Soil, depending on its composition, can be low or it can be very, very high. And then we look over here. Snow and ice are actually very, very high. But keep in mind their temperatures. Their temperatures are very, very low, so you wouldn't expect them to emit much radiation. And then things like coal and black paint, these darker objects, compared to what they absorb, they are very good emitters. Okay, another aspect of looking at the temperature on the surface of the Earth is the surface heat capacity. And again, we're going to relate this back to what we talked about in our thermal energy unit, talking about the specific heat capacity. And it's the specific heat capacity and the surface heat capacity, we're talking about generally the same thing, except when we're talking about surface heat capacity, we're talking about the average energy that it takes per square meter to change the temperature. And so, across the surface of the Earth, what is the amount of energy per square meter needed to raise the surface by some degree, by 1 degree Kelvin? Now we mentioned that the sun drops about 340 watts per square meter on us, but each surface has a different heat capacity depending on what the material is, and that makes sense. Most of the thermal energy, though, the sun that the Earth stores from the greenhouse effect is stored in the upper 70 meters of the ocean. And you remember back we talked earlier in these notes, we said that the albedo of water is actually fairly low. It absorbs most of the incident infrared radiation. It doesn't reflect much. And so all of that water, again, it has a very high specific heat capacity. Remember what we know about water, high specific heat. It absorbs a lot of that energy and it stores it there. And so a lot of the energy from the sun gets stored in the oceans. And it also, of course, is because most of the surface of the Earth is ocean, it's water. And so most of the sunlight that hits the surface of the Earth is going to be hitting water. And so a lot of that thermal energy gets stored in the water. Now, because there are so many variables, because we have albedos and we have emissivities and we have different surface types and we have such a diverse surface on our planet, it's really difficult to accurately predict climate change and what's going to happen. And scientists try and model it. They try and develop what we call energy balance climate models. And essentially they try and simplify all the things going on with the environment to get an idea of what could happen or what may happen to the climate on the surface of the Earth. And that's where you get a lot of these kind of doom and gloom forecasts coming from, is that some scientists run some specific type of climate model and it says that the world is going to end in earthquakes and typhoons and we're all going to burn and that kind of thing because of global warming. It's because somebody ran a specific projection, used a specific model, and got this specific data. And then you might have somebody else that runs it that says in 1,000 years we're going to be in the midst of another ice age. So it's important to understand that whenever you look at one of the climate models and one of these projections, that you realize that different models take into account different things and put different emphases on different variables to determine what they think is going to happen. But it's an important part of climate science and climatology is that we have these models and then we work through these models and try and figure out what variables are going to be the most impactful. One of the simpler ones, the energy balance climate model, though, just tries to kind of look at energy coming in, energy going out, and it's one of the simpler approaches, but with everything, it's sometimes simpler is better. Because now in this specific type of model, we only have one variable. And that's just the amount of incoming and outgoing radiation. Now, this is a very simple model, but there are also many, many more complex models out there and available to look at.